All right, so welcome to today's lecture. We're starting the last chapter and finishing the last chapter this week, 6, on inertial sensors, which means acceleration sensors and gyros, rotational angular rate sensors. So the quantities we would like to measure here are related to coordinate systems. If I draw a coordinate system, X, Y, and Z here, and let's say this is the reference system. And then we have another coordinate system that moves with respect to this object at a speed and a velocity vector, which I'll draw just like this vector v in this direction. One might be tempted to ask, are we moving? Is an object, a system that is somehow fixed to this coordinate system, is it able to detect its velocity? No, it's a deep physical question, and the answer is no, because there's no way to determine whether one is at rest or in motion in the form of a constant velocity, because viewed from this coordinate system, the other coordinate system is in a relative motion with a negative velocity, and there is no way to distinguish. There is no absolute still point. There is no absolute coordinate center in this universe to say this is at rest and everything else moves. So we only can observe relative velocities, but just by some internal measurement, it's not possible. However, it's possible to detect an acceleration with respect to one of those steadily moving coordinate system. A third coordinate system might be accelerating. So let me draw this little object here, and this object is now accelerating with a velocity a, and that one is able to detect. One is not able to determine what the origin of that acceleration is. Is it because I'm acting with a force on this object against the inertial parameter of this object, its mass, to accelerate it according to F equals m times a? So am I acting with an external mechanical force on it, or is this force due to gravitation? This is what is called the equivalence principle, and Einstein used that to start developing his theory of relativity. But one is able to measure that acceleration, whatever its origin. So the astronaut in an elevator called rocket out in space, being accelerated, if he's not hearing any sound because it's all insulated acoustically, he cannot detect whether he's on the Earth being accelerated towards the Earth at 1g, or whether the rocket is accelerated because it thrusts out some mass and accelerated. So this is definitely not possible, but the effect of this acceleration, that the cheeks hang down and everything, that is detectable. Now, if we talk about rotations, this coordinate system, this original coordinate system, X, Y, and Z, might be rotated. So it might be in a state of rotation around some vector, which I'll draw here now, some obliquely. So it's being in a state of rotation around an axis. And this motion can be uniform. And unlike the velocity, where the motion is also uniform, this uniform rotational velocity, rotational angular velocity, can be detected. So this can be detected, that can be detected. And of course, if there is angular acceleration, so kind of if I call this motion by some vector omega, and then here this omega vector is actually changing with time, so the thing spins faster and faster and faster, like Denise Billman, you know, retracting her whatever, you know, this was an ice skater champion from Switzerland in my earlier times, and she invented the Billman pirouette, where she pulls her leg up in the back and then holds it up here, and then yeah, and so at some point the angular velocity becomes faster and faster until it reaches supersonic velocities at the surface, and then she calms down again. Yeah, boom, and so of course this can also be detected. You only have to detect the change of this. Yeah, so there is a bit of a change, and this chapter is about measuring accelerations and measuring these rotational angles. And so I'll first start with the acceleration sensors. So all these sensors able to detect those detectable motions of coordinate systems are called inertial sensors. And very often now, inertial sensors are integrated in very small packages with acceleration being measured in 3 directions and rotational angular rotation being measured also along the 3 axes. So 6 degree of freedom measurements are the state of the art and very current now. And so let's start with the acceleration sensors. So an acceleration sensor is based usually on the inertia of a mass. A mass being held in a coordinate system that now I call Z. Yeah, so this has nothing to do with the 3 directions, X, Y, and Z. These are just positions in a one dimensional setting, so horizontal setting, and I'm just calling the position of the substrate Z. If it moves, then Z increases. The position of this mass is called Y. If it moves, Y increases. If Z moves faster than Y, then of course this object here, symbolizing a spring with spring constant K, you know, is compressed, yeah, and will exert a force on the mass. Now, so the acceleration of the substrate will be felt by the fact that this spring is contracted because the mass wants to stay where it is, and then the inertial system given by the substrate pushes on the spring, and then the mass gets accelerated. And if the acceleration continues and continues, this spring will continue to be compressed, and that effect is exploited in accelerometers. Now, this is not the only thing. There is also usually what is called a damper, symbolized by this constant D, the damping constant D, which says that this mass wants to kind of take back the original position. The force K wants to, the force due to this spring element wants to expand again and put the mass at rest. But if it was just a K and a mass, then the mass might just oscillate back and forth. And in order to have, again, this stable position, one adds consciously or just by construction, maybe there a damper with a constant like that. And so these, what happens is now that one wants to measure this acceleration of a substrate. This could be a car, yeah, a car moving at constant speed, and then at some point it hits an obstacle, another car, and then there is a sudden deceleration, which is negative acceleration, and this mass of the sensor wants to continue its journey, and therefore the collision is being detected by the expansion of this spring constant of the spring, and the airbag will be inflated, saving the person from being injured. And so what happens here? this relative position of y with respect to z needs to be measured. Yeah, so x we call the difference of y minus z. So if y minus z is positive, it means that the spring is elongated. If it is negative, it means that the spring is compressed. Yeah? And so the spring force acting on this mass is k times the length change. If the spring is compressed, z minus y is positive. The mass has moved less than this other side of the spring, and then the force is positive. Now I apologize here. I saw yesterday that there is this mistake, a minus sign that needs to be added here. Yeah, x is y minus z. So that's the definition according to this picture. So we need to write minus kx here. Yeah, and so this is one element. The other element is the damper, which has the effect that if those two sides move at different speeds, there is also a force. So you can imagine this as a pot of highly viscous material. So if I push with my piston in this viscous material, the honey, the technical honey, the honey pot wants to move away because there is friction within this viscous liquid and energy dissipation by the relative motion. So this speed of the piston gets transmitted as a force onto the mass. It's proportional to the speed of the piston, so it's proportional to the relative speed of z with respect to y, which is translated into a force, and that speed is, of course, the time derivative z dot dz. So this is dz over dt, and this is dy over dt, and then again we need to add a minus here. If z moves faster, then the piston gets compressed, and that means a positive force on the mass. And this is, of course, also dx over dt. And so now the motion of this mass is mass times acceleration. Acceleration of the mass is y dot dot, the second derivative. And that acceleration times acceleration, that mass times acceleration is, of course, the sum of the two forces that are acting, Fk, spring force, and damping force. And if I just, insert these forces in here and then, put the things on the right side, I end up with an equation that tells me how x, this relative distance, evolves as a function of time if this substrate moves according to a certain time function, a certain acceleration. So the situation is that now we have an expression that says, okay, if the substrate accelerates or decelerates according to this function, then we can determine how y minus z behaves as a function of time. And this is a very well-known equation. If we just consider the first part equals 0, it would be the so-called free harmonic oscillator, the damped free harmonic oscillator. And with this external force here, due to this, it's like an external force, this minus mz prime prime, it's the driven damped harmonic oscillator. If it were not damped, then this d would be 0, and then we would have a pure oscillator, and here we have a damped oscillator. And so if I now summarize my z dot dot just as what it is, an acceleration, the acceleration of the car, then I can write this in this way. I can divide by m, and then I have my second order differential equation for x dot dot, and then x prime, or x dot and x with coefficients, two coefficients d over m and k over m. Yeah, and then on the right-hand side, the condition to which the object is subjected, and that's this acceleration minus a. And so we look at this equation and then we ask, how do we solve it? And that is fairly easy. Yeah. So if I'll just summarize that that solution path. One says that x of t is equal to some amplitude. Let's call it a times a times maybe some phase, times e to the I omega t. So with this, I can insert this into this left-hand side, and then my acceleration actually, for what acceleration am I solving this? This is of course a function of t. So supposing we have a of the form a of t of the form a0 times e to the I omega t. So when we insert this ansatz into this equation, it will produce something like ai to the phi multiplied by minus I omega square. That's the second derivative, coming down here twice. This I omega pops down, and then this is multiplied by e to the I omega t. And then, so that's the first term. The second term has dm d over m multiplied by x prime, which is a e to the I phi times I omega only once, in I omega t. So this is this was term number one. Now we have term number two, and now we do term number three. So this was one, this was two, and now we are doing number three. This k over m stays here, k over m times a e to the I phi, and then nothing, and e to the I omega t. And these three summed together must be equal to a0 with a minus times e to the I omega t. So once you have established that equality, this plus this plus this is equal to that, you can start simplifying. So I'm doing that in another color. I'm just crossing out all the e I omega t's. And then I can also, that's pretty much it. I can also extract some prefactor. So I can also say, okay, this is a e I phi, some complex prefactor times, and now I'm also doing a change of sign. Sorry, that was too fast. This minus I to the square produces I to the square, which is minus. So minus omega square plus I omega plus times d m over m plus nothing, k over m, close the bracket, is equal to minus a0. And then one observes this this solution. So omega is the frequency, the angular frequency at which this acceleration happens. The substrate shakes with angular frequency omega, and then we want to observe how the relative coordinate moves as a function of that driving force. And that response is encoded in this amplitude, like the acceleration is encoded in this amplitude. So here is the amplitude of x. So this is the amplitude factor, and this amplitude has some number times some phase factor, and then you see how this changes as a function of frequency. This is definitely a frequency dependent object. So A times EI phi are functions of frequency. And if I write that again, we'll need that on the next page. This is equal to A0 over omega square minus I omega. And now this D over M is abbreviated. D over M is abbreviated as omega 0 over Q. Well, I first introduced the omega. I can write omega 0 square. So this omega 0 square takes over the role of this K over M. And so omega 0 is square root of K over M. This is the natural angular, the natural resonance frequency of the mass under the effect of this spring constant. If we only had this mass and only the spring constant and we pulled on the mass, it would oscillate at this angular frequency omega 0. And then we have this other term D over M, which can be written as omega 0 over Q. So this is usually written omega 0 over Q, where Q is the so-called quality factor, which can also be now, of course, implemented here. Omega 0 times M over D. And then we have here K over M over D, of course. So what we see is that the amplitude and this phase, this prefactor of the responding motion depends on the frequency. And this frequency becomes, or this denominator here becomes, of course, very small when omega is close to omega 0. Then those two cancel, and then the only thing that remains is this maybe small number. So this is a strong function of frequency, and we can look at this function of frequency on the side. So here I have A over A0 in this plot. And this is the resonance curves that you know from such oscillating systems with springs and dampers. So what is happening here? Okay, now here we see it again, A0. So A0, being given, the amplitude of the oscillator is amplified in some locations by a significant amount. And that significant amount depends on the Q factor. So the quality factor says how much this motion actually is amplified. It needs very little for a weakly damped oscillator to be excited into large motions, because each time when you kind of shake it back and forth, it absorbs energy, and then its energy absorbs, and at some point its motion is so large that what it loses per cycle into the damper is equal to what you invest in it by shaking it. And that happens at a larger and larger amplitude if that Q factor becomes larger and larger. That's why it's called Q factor. The quality of the oscillation is increased if Q is larger. And so let's look at the Q. Q is large when D is small, when the damper is inefficient. The larger the damping is, the smaller the Q factor. So that's one important parameter. And that Q factor is also visible in the width of this, this delta W in comparison with the with omega 0. So these are the amplitude curves, and these amplitude curves are shown here, and I have to correct this again. There is a minus sign that is wrong. So the equation that we have down here is this complex number is equal to this frequency dependent complex number. Just the same thing as is written here. And now, of course, we can say, okay, what is the absolute value on the left? The absolute value on the left is just this prefactor A. And here the absolute value of this complex function with its I, what might it be? Well, we just do a complex conjugate multiplication on the numerator and denominator. So we multiply the bottom with omega minus omega 0 square plus I omega 0 over q, and do the same on top. Yeah, and then the bottom here is just the absolute value squared, and actually it's yeah, that's one way to do it. And then we so actually the absolute value of this thing is just the square root of this real and this imaginary part added here as squares. So that's what is done here more directly. And but this complement idea also works, of course. And then we also have a way to calculate this angular, this phase factor. This phase factor is, related to how much imaginary component there is in this part. Yeah, the phase factor is nothing else than cosine of phi plus I sine of phi, and of course this complex number. Once we did this complement, we have also a real part, and we have an imaginary part, the real part being here and the imaginary part being here. And if we then calculate the tangent of phi, we do a division of the real part and of the imaginary part divided by the real part, and what comes out is this quantity here. Yeah, so that then so this is equal to omega 0 over q divided by omega 0 minus omega minus omega 0 squared. And then this is the arctangent is applied on the left and the right, and we have this expression of this phase angle as a function of the frequency. And that phase angle has also a characteristic form for these harmonic oscillators, these driven and damped harmonic oscillators. So it's an angle that goes from 0 degrees to 180 degrees at high frequencies. And this S-shaped curve becomes flatter and flatter the smaller the Q factor is. You can imagine that if I'm driving an oscillating system at low frequency, so the M, I'm the substrate, and here is M connected to me by the spring. If I do that at low frequency, it is able to follow me. So first of all, the ratio of the motional amplitudes is 1. That's what it says here at low frequencies, 1. And the relative phase is 0. Both move in unison. And then if I go at very high frequencies, actually, or let me accelerate the frequency now. So this is very slow, and now I'm going faster and faster, and I have the spring between my arms. I'm trying to play mass and substrate and spring at the same time. So yeah, it is able to follow, and the damping is not so large, so it does this. Yes, so here I am again. It does this large motion, and so you see that there is it's neither in unison nor antiphase. It's just at 90 degrees. And then I'm accelerating more and more, and then the mass will move, will shake little, and it will shake actually at 180 degrees with respect to the driving force. And that's this transition from 0 degrees to 180 degrees at large frequencies. Note that the frequencies are here denoted by omega in units of omega 0, because that's the natural frequency of this harmonic oscillator. So now, how is this applied in a real sensor? Yeah, we see here a capacitive accelerometer from Bosch, one of those accelerometers that is in their inertial measurement units, or was in their inertial measurement units. They look still pretty much the same. Yeah? So what do we see here? Complicated structure, isn't it? Yeah. Let me leave some space. So what we have here is an object that looks like a spine, a spinal cord, and then there are ribs attached to it. Yeah, so these little ribs that protrude sideways, those are all attached to the central component. Yeah, this central component represents the mass. The spinal cord plus some additional pieces of mass, maybe here and then a little bit here. And then this mass is actually suspended. So here is substrate, and here is also substrate. And then we have some springs. Now those springs, so here is anchor. A substrate is called anchor here in this picture. So this is the substrate. This part is attached firmly to the chip in the back, which is packaged and which is attached to the car. And so the car, lets this anchor point move according to the acceleration of the car. And now on this anchor point, we have some springs that are these folded flat spring elements that fold back and forth, kind of like a bellow that you can pull in the length or compress. And then here it goes around the corner and then into this horizontal piece, this spinal cord. And so all this element down here, including this thing up to here, you could think of it as a spring, and then there are more mass pieces attached to it sideways. Now those sideways elements are electrodes that need to be attached to sense its motion. So we have the central so-called seismic mass. That's how accelerometer developers talk about their mass. They say this is the seismic mass. It's the thing that is able to feel the shakiness of the surrounding. When the surroundings shake, we have a seism, an earthquake. Seismic means earthquake mass. Seismic mass. And so that's the part. And this spring element, of course, I mean, these are pieces of solid material that get deformed. So they have an elasticity, and we need to quantify that elastic property when doing the reverse engineering of the structure. These other elements are just attached to the spinal cord. These ribs are only attached here, and they are fairly rigid, and there is nothing that pushes on them on the other end. They are facing, on the other hand, two sorts of electrodes. One electrode on this left side, and another electrode, maybe it can be shown here in green. I don't know if it shows up in my back, but here we have this green element on the other side of the electrode. And so these electrodes can be viewed here. We have the yellow ones. For every electrode rib, we have a yellow electrode, and then we have all the green ones attached to the same part here. Those are fixed mechanically on the chip. They don't move, but they are electrically insulated from each other. Insulated, they are connected to each other. All the yellow ones are connected to each other to the same potential. So there is a V counter electrode 1, and then there is a V, that could be a V counter electrode 2. And then we have, of course, here, this object here is also at a potential, the V of the seismic mass, or the V of the electrode elements, the blue electrode elements in the middle here. Yeah? So you may also wonder why these electrodes are designed like this, like these fine ribs, highly machined structures. That the reason is that well, the mass needs to be light, yeah, and therefore removing as much material as possible makes sense. You also see that material has been removed here in this spinal cord, in this central frame element, yeah, where a complicated structure with all kinds of holes has been realized, so that there is as much rigidity for as little mass as possible. And this was done by deep reactive ion etching. There is this layer of silicon, Bosch's so-called epi-polysilicon, which is a polysilicon grown at high temperature, like an epi-silicon that is usually grown on a silicon wafer. This is grown on oxide to a thickness of maybe 15 micrometers height and can be trenched by deep reactive ion etching into these structures. Yeah, so everything you see black is a vertical trench that goes down to the oxide, and in some places the oxide is removed, so the structures are suspended over nothing, can move, and there, for instance, this seismic mass element is only suspended at the anchor points. That is a large structure that does not get under-etched when you remove the oxide underneath, whereas all these thin structures, of course, get under-etched because the etching distance is so short. Same for the spinal cord in the middle. Yeah, and likewise, these electrodes get under-etched also, certainly along the side, but not where they are attached. Okay, so now we got at least two things. So let me maybe write here. Here is our K. Yeah. So this spring here we also have spring. Here we have also spring. Here we have also spring. These are 4 spring elements that resist the displacement of the central mobile mass, the seismic mass. And because, it's attached on the other side on the anchor, and the rigidity of that structure then determines what is the omega 0 of this structure. Yeah? So now you may also wonder, where is the damper? Yeah? Is there any damper element? Where is the honey? Yeah, the viscous material. Well, the viscous material here is air. If you think of all these vertical plates, these blades, spring blades and electrode blades and counter-electrode blades, those are all long, slender beams, 15 micron high, and then 2 micron wide or 3 micron wide, with gaps of 2 micron. If they move with respect to each other, they squeeze out air. Yeah, so if I go, this air is expelled. If I pull apart, air has to flow in, and that costs energy. Yeah, that is viscous material, and it's done everywhere. So this is what is called viscous air damping, or squeeze film damping. Because the film of air between these plates is squeezed, and that causes viscous energy losses, which correspond to the damper. So the dampers are everywhere. Yeah? So I don't expect that Bosch is evacuating their package in order to make it as good, as high Q as possible. Yeah? Because they want a certain time constant. The Q determines how fast a free oscillation decays. You drive something into resonance, and then you let it resonate for itself. How long does it take until the object has again as the oscillation has decayed? Or how long does it take for an oscillation of one amplitude to transit to an oscillation of another amplitude? That transition is modeled by the Q factor, and the time it takes has something to do with the time constant of one oscillation, and then usually you can just multiply it by q to have an order of magnitude of the exponential transition from one state to another state. And so if a car is expected to detect an acceleration within a millisecond, a millisecond hitting a tree or another car at speed of 20 kilometers, against something standing still, boof, a millisecond is a short time, but it's maybe it's long enough or short enough for your face not to have yet reached the steering wheel. In this millisecond, the endangered person's face has only moved by maybe 10 centimeters. Well, you can calculate that, and then boom, inflates the bag, and you're safe. So these are the time constants that need to be taken into account in the calculations of such accelerometers. And so what else do we have here? Interestingly, we have here another fixed part. That's a so-called stopper, and the mobile part can move back and forth, but not too much. So if you see the gap between the mobile part and the stopper part, there's a little gap here. And if now the mobile part moves by more than this gap, it is arrested. It is stopped by the stopper. So this is kind of a bumper between structures. So the mobile mass does not just fly off under some excessive acceleration. It is just bumping into the other side. It's an art to design these stoppers. So this is not the newest version, because objects bumping into each other cause fracture, debris, blockage, everything. So usually after, a really hard event has happened, you replace the accelerometer. You put in another one because you don't know what happened. But anyway, there are many ideas to cause stoppers that move less violently into each other, more smoothly, that make sure that this stopping somehow does not cause excessive overloads of the material. So what I'll next do, I think, is to analyze the spring. So the mass can be calculated based on cross-section. One looks at the area and then dimensions, and then one estimates the mass. Actually, I think I estimated the mass here to 2 times 10 to the minus 9 kilogram. 10 to the minus 6 gram. So it's a microgram. That's the silicon, the piece of silicon that moves here with all its fins and everything. Microgram, 2 microgram. And now we would like to know about these springs. So what do we have here between this location and this location? But what kind of spring do we have? We have a spring that is shaped like this. It goes, so from its suspension, it goes up and then down again, and then up again and down again. And then it is fixed on the other side. So elongated, this would look like something like this, highly exaggerated. Now you see that there has been, from the original distance, from the equilibrium distance, let's call this D0, there has now been D0 plus some significant delta D. And this expansion now of this structure is analyzed on this page. You see only one of those zigzags being pulled apart by a force. And that pulling causes this beam material to to bend and then to bend back. And here in this corner structure, it ends horizontally. Yeah, and then it continues again horizontally to bend and then bend back into the horizontal part that is now in this intermediate point. And of course, several of those, two of those zigzags are attached to each other, but at the end, there is then the spinal cord, and at the one end, there is the anchor point. So it's enough to analyze this single element here, and then to multiply it by 4. In what sense? Under a force F, the single element will be deflected by some W, L, at this position L. The length of the spring element is called L. Yeah, and then if we have 2 of those, it's 2L. If you have 3 of those, 4 of those, it's 4L. Yeah? 4WL. Under the same force. Yeah? Here also the force is acting in this direction. Yeah, and then of course there is the counter force, and so Aktio gleich Reaktio. Yeah, and so we can basically consider this one spring element, and that one spring element has to fulfill a differential equation that is quite simple. It's the 4th derivative of the deflection function W of x. That must be equal to 0. Yeah? Because there are no forces inside, there are no moments inside, and so that's the beam that only has end forces and end effects acting on it. So there is a force, but there is also an angular momentum to make it here flat. And the solution of that differential equation under the appropriate boundary conditions is easy to calculate. It's the 4th derivative. So this it's kind of awkward. I should write d4w over dx to the 4. So that is equal to 0. And the stiffness parameter that is important here is E times I. E, the elastic modulus, and then I, this is the cross-sectional moment of inertia, which is given by H times D to the cube divided by 12. D is the thickness of this structure that is being bent. It's the bending thickness, or the thickness of the material in the plane of the bending. And H is the thickness of the material in the out of the plane of the structure. So this is a structure that has a height, and this height is called H. And of course, the cross-sectional moment of inertia is proportional to this H. And so when I look at this equation, I need also some boundary conditions. And that boundary condition for this beam is that actually at this location x equals 0, it is not deflected. It is flat. Okay, that's the second boundary condition. And then at this other end at L, at x equals L, it is also flat. So the derivative of W with respect to x at L is 0. And then I can also, add a 4th boundary condition by the fact that this force F that is now working on this piece of material, this F causes, of course, a moment at this point. So you pull with F a distance L away from this suspension point, and that corresponds to a moment which this piece of material has to resist. And that moment is F times L. The torque is F times L. And here is where E times I comes into play, because the torque causes a bending. Bending is second derivative of W. And the stiffness with which this object resists bending, the stiffness is given by E times I. So the stiffer the material is for a given torque, the less the beam bends. The larger I is the inertial cross-sectional moment of inertia. The larger I is, the less the structure bends. And that is the case when it is thicker, yeah, because I have force per thickness, yeah. Thicker, the force distributes over a a deeper, yeah, or higher beam, so it will bend less. And if the beam becomes thicker because D becomes thicker, then it resists the bending also better. And it does so with the cube of the thickness. That's an important law. You know, beams respond to mechanical forces with the cube of the thickness. You make a beam 2 times as thick as an original beam, it will, under the same force, it will deflect only 1/8 of the original beam. Yeah, so here we have these 4 boundary conditions which we try to solve, and then we do just an ansatz where we say, okay, W0 is equal to let's call that constant 0 plus constant 1 times x plus constant 2 times x squared. Yeah, and how far do we have to go? Well, we can go up to a cube. Yeah, and then the 4th power we can't have because then the 4th derivative wouldn't be equal to 0. So with these 4 coefficients, unknown coefficients, and that law of deflection, we are able to fulfill these 4 boundary conditions. And then once we identified those values of C0 to C3, we insert them and we find the solution as it is really standing there, namely W of x, the deflection as a function of this horizontal coordinate is equal to this function, and this function is given by this expression here. So if we just look, if it might fulfill the boundary condition, W at 0 is equal to prefactor times 0 minus 0, 0. Okay, that's fine. Yeah. The derivative pulls down factor of 2 here, leaves x. Okay, and then here it pulls down the factor of 3, and it leaves x squared, evaluated at 0, 0. Okay, so second boundary fulfilled 0. And you can go on to the last boundary condition, and you will find that all 4 are fulfilled. Yeah, so now we have the shape of this deflection. And as a consequence, we also have the deflection at the end. W at L is equal to F over EI multiplied by L times L squared, L cubed divided by 2 minus L cubed divided by 3. That's L cubed divided by 6. A sixth. Half minus 1/3 is 1/6. So that's easy. And now we can calculate the bending, the spring constant of this thing. The spring constant is called force per deflection, force per length change. So K is usually represented as, with springs as force is equal to K times the elongation of a spring, delta X. Now here the elongation is kind of in this vertical direction, in this W direction. But there is, in response to F, there is a certain delta X, and that delta X we identify with W of L. So we can calculate F over deflection, F over W of L, and then this must be equal to 6 EI over L cubed. And when we insert I, we obtain this other form, this final expression, which we can then evaluate with given dimensions and an elastic modulus. So I did that here in my attempt to reverse engineer Bosch's sensor. We have a height of 15 micrometers. That's typical epi-poly thickness. Then we have beam thicknesses of these bending beams. By looking here and then it's evaluating and so on, I said, okay, this must be 3. So it's a smart guess, 3 micrometers. The length is 200 micrometers. Might that be true? If this is 100, then this might be 200. Okay. The elastic modulus is that of silicon. So let's take some average value. It's polycrystalline anyway, so It's somewhere between 130 and 168. So let's take 150. And by inserting these quantities, we obtain K is equal to 4 Newton per meter. So in order to deflect that part by a meter, we need to apply 4 Newton. We will never apply 4 Newton. Yeah, we might apply 4 micronewton to deflect it 1 micrometer. 4 micronewton per micrometer makes 4 Newton per meter. Yeah, so a deflection of 1 micrometer causes or costs 1 micronewton of force. And now we have these 4 beams, one after the other. So I'll just schematically draw the other ones as well. So schematically, and now we have here, let's say maybe the spinal cord. Here is anchor. So what is the spring constant of this compound spring? Force per deflection. The deflection is now 4 times as large. So the spring constant of this 2 times folded spring is going to be 1 Newton per meter. We only need 1 Newton to deflect this end here by 1 meter, or 1 micronewton to deflect it by 1 micrometer. That's fairly easy to understand. If there are, however, parallel springs, these springs are in series, and so their spring constant is divided by the number of the springs. Here we have also parallel springs. We have 1 spring on this side, second one on that side, same construction, just mirrored. And then on the left, we have the same again. So we have 4 identical elements that act as spring, that all act at the same time against the motion. So those are now in parallel, and the spring constant of parallel springs needs to be added. You have to push against 2 springs, means it's harder to deflect it. In the fitness gym, if you have 2 weights pulling, it's harder. So this is what happens here. So overall, those 4 parallel groups of 4 springs in series, 4 of those blade springs in series, makes an overall K still of 4 Newton per meter. Divided by 4 and then multiplied by 4 makes 4 Newton per meter. So the mass I estimated to 2 times 10 to the minus 9 kilo, which means that for an acceleration, not in resonance, for an acceleration, the deflection is going to be K over M. Well, how do we get this result? So what is, if I just transform this to show where it came from, I can write this as strange. I wonder if there is something just, I should, let's see why. It should not be to the minus 1, M over K, because we would like to have K times delta X is equal to M times acceleration. Force, spring force is equal to acceleration force, inertial force. So I think there must be a minus 1. I didn't notice that on the weekend. And so if I calculate now M over K, I have this ratio of delta X over A, and the result is 0.55 Newton meter per second square. So for any unit of acceleration of 1 meter per second square, I get a deflection of 0.55 nanometers. Okay, so if I apply 50G, 50G, 1G is what we experience here. Now imagine that multiplied by 50, that would be 50G on Saturn maybe. Then the deflection would be 270 nanometers. 50G is 500, roughly 500 meter per second square. So this multiplied by 500 makes 270 nanometer. And 270 nanometers may be a reasonable choice in view of the dimensions of the gaps. So under 50 Gs, those gaps will not be closing totally. 50 G is not going to be too tough on that structure. So it may easily survive 50 G, and those electrodes will then deflect by 270 nanometers to one side, all in parallel, getting closer to one counter electrode by 270 nanometers, and then farther away from the other side by 270 nanometers as well. So that's interesting. Why 50 G? That's the typical impact in an accident. Oh, you hear it, yeah? You hear 50 G in cars, yeah? And so that's a typical number that is important in the automotive acceleration sensor business. If you do inclinometry to determine where it's down, like in an iPhone, to determine whether the picture should be rotated or not, yeah, you're measuring 1G, 1G, 1G. Yeah. Now you can start trying to fool the system by accelerating it sideways, to make sure that it feels this acceleration as more than 1G. Then it will say, "Oh God, yeah, the acceleration comes from this side. I should rotate my picture." Yeah, try to do that. 1G is a lot. 10 meter per second square is a large acceleration. Yeah, it's like falling on the floor. Falling down from some height. So I think this experiment can't be done with your hands. But it's just a thought experiment. Yeah. Now let's talk about the resonance frequency of this structure. This mass with this spring constant, it's going to be 7,000 hertz. 7 kilohertz. And that's enough to react within 1 millisecond. Yeah. It has the bandwidth that is required to detect signals that occur with changes within 1 millisecond. Yeah. Now the other element is now these capacitors. We need to understand these capacitors. So we have this seismic mass on one side, and then we have these electrodes attached to the seismic mass, and then these two pairs of counter electrodes on each side of these mobile electrodes. And so you can imagine that a measurement of the deflection of this seismic mass with respect to these counter electrodes might be done in a first measurement by just measuring the capacitance between central and one side of the counter electrode. If you detect that this increases, then you will know that the distance becomes smaller. If it decreases, the distance becomes larger. So that is something. You can also do a second kind of measurement. You can apply a voltage between those two electrodes, the counter electrodes, let's say 0 volt and 1 volt. And then you let the potential of this central electrode float between the two. It has to adapt to wherever the electrode is. If it is closer to 0 volt, it will take a smaller voltage. Charges will have to be evacuated, and if it moves more to the right electrode, it will have a voltage that is closer to the 1 volt on the right hand side. So detecting the voltage of this floating electrode that takes whatever charge it needs to get that potential that it should have in between these two potential boundary conditions is another method. Now, so let's look at the capacitance. What capacitances do we have to measure? So capacitance is equal to number of gaps times epsilon 0 times the cross-sectional area of the electrode plates. Here it is height times length, age times length. And then the electrode also implements, of course, the capacitance also implements the gap, of course, in the denominator. Yeah, so this is the standard capacitance formula for a parallel plate capacitor. And we can now determine that N is 44. I tried to count those again. Yeah, I was a bit surprised. So if I count these yellow pieces here, I get 22, and with 22 more down here, 44. Okay, so it's quite easy. Yeah. However, if I count the electrodes attached to the spine, I only see 21. And then there is, I don't know, this thing out there. Should that count also as an electrode with respect to that? I don't know. Yeah, could be. Yeah, so it's either 42 or 44. N is 44. Epsilon 0 is how much? That's the permittivity of vacuum. 8.85 times 10 to the minus 12 farad per meter, I think. And then we have our dimensions. L is now 150. I estimated that length to be a little bit smaller. Yeah, so this length is smaller than the spring length of 200. I said 150. And then I said, okay, the thickness is still 15 micrometer and the gap is 2 micrometers. Yeah, so with those numbers, you estimate the capacitance to be 4.4 times 10 to the minus 13 farad. 0.44 picofarad. So that's not a large capacitance. And then the sense, now we can define a sensitivity, which is the capacitance change per motion per shift x of that mass. If that shifts by x, the change of capacitance per x is equal to capacitance. Well, if I write, of course, delta C over delta X, that's the shift of the capacitance per shift of the seismic mass. But of course, infinitesimally, I will write this as dC over dx. And X here is, of course, d gap plus some delta X by which this mass indeed moves, and let me write here rather delta X. So if it is addressed here and then moves to here, and this is delta X, then if it's infinitesimal, we can just call it dx. And we take this formula here, and this derivative is just C. One does the derivative, and that because this is just a 1 over d, then 1 over d becomes 1 over d squared with a minus, and so the power of -1 becomes -2, and that's just like dividing C by the gap width. And if we do that, then we can calculate here the value of 2.2 times 10 to the -7 farad per meter. So it's per meter of gap change, one has a capacitance change of 10 to the -7 meter farad. Of course, now it's here maybe nanometer, and then that makes it nanofarad. 2 times 10 to the -7 nanofarad per nanometer of shift. So you see that these changes can be quite small. So for instance, if I now translate that into a capacitance change per acceleration per meter per second, I can do dC over dx times dx over dA. Sorry, badly written. This we already have. That's SD gap, the gap-related capacitive sensitivity. And this is now multiplied with dx over dA, which we already have from before. This is m over k, x over a, m over k. Yeah, here it's now correctly written, m over k, c over d gap times m over k. And that translates into 1.2 times 10 to the minus 16 farad per acceleration unit per meter second. That's a small number. And even if it's measured in G is, of course, 10 meters per second. So this increases by a factor of 10. The farad per G are 1.2 times 10 to the minus 15. So we need a powerful C measurement in any case. These micro-machined accelerometers require a lot of circuitry attached to them to extract those little capacitance changes. And so in the case of measurement 1, of course, one has only one side where it increases, another side where it decreases. So one can do some offset compensation and maybe has a factor of 2 to calculate, but roughly that's what one can expect. On the other hand, if we measure this voltage-related thing, where we detect the voltage as a function of the motion going from 0 volt to V in on the other side, then we can also calculate a voltage-related sensitivity per gap change, which is dV out over dx, which is V in over 2 times d gap, and that can be estimated to be 2.5 times 10 to the 5 volt as a V in volt per meter. So if we put in 1 volt between those two counter electrodes, here 0 and 1 volt, then we will obtain 2.5 times 10 to the 5 volt per meter of change, or microvolt per micrometer change of horizontal motion. And again, that can be translated into the acceleration related sensitivity, which is again related to the first one by m over k, which is 1.4 times 10 to the minus 4 times V in units of volt per meter and second of acceleration to which this is exposed. And if it's G, well, it's again a factor of 10 larger. So for 1 G, one will detect a voltage change of 10 to the minus 3 millivolt times, or milli times the input volt. 1 volt in means 1.4 millivolt voltage out per G of acceleration acting on that system. All based on these estimates of the spring constants and the masses that I gave you. And actually this this methodology is followed by the example that I will show you later by Analog Devices. One of the first companies who produced CMOS compatible accelerometers. Bosch does that, of course, now also, but Analog Devices was there already in the 90s and actually late 80s. So then also with all these systems, of course, noise is important. And unfortunately, you already know part of what is repeated here. So if you have some capacitance, and some resistance, the resistance will cause some voltage noise, some white noise or Johnson noise, and that is going to be influenced by the capacitance that short circuits part of those noise contributions, and more so if the frequency is high. And so over the capacitance, one will measure Vn, some noise voltage over the capacitance. And we have seen how to calculate that. Vnc over Vnr is equal to the transfer function of this voltage divider. We have a voltage source here, and then we have a voltage divider that goes via an R and a C to the other side of the voltage source. And then we would like to know only the voltage over the capacitance. That's a voltage divider, and that has a transfer function given by 1 over 1 plus what is written here, 1 over 2 pi f RC. RC is the time constant of this RC circuit. And then the absolute value of the noise voltage is equal to, and here is an error, that should be a multiplication sign, or it should just be absolute. It's the absolute value of HF multiplied by V and R. And so if V and R is effective over some frequency range delta F, we know what V and R is, the spectral noise voltage density. It's 4 kBTR, which then gets multiplied by delta F. And if we now calculate V and C, now as if over all frequencies, so if I integrate that over all frequencies, it's just like integrating HF multiplied with this constant noise voltage density, V and R, and then this integral can be carried out, and the result is KBT over C, as we have already seen. So the noise voltage here, integrated over all frequencies, summed up, stochastically, produces a voltage that on average has the square value KBT over C. Independent of the R, as long as this upper limit is larger than the frequency corresponding to the time constant of this RC. And so, for instance, if we ask how much energy stored in such a capacitor, just because it is at temperature T, then this can be calculated like the usual formula. The energy stored in a capacitor is equal to 1/2 C times the voltage square, or should I say energy, energy of this capacitor is equal to 1/2 C per V square. Well, here's your V square, here's your C, here's the 1/2, and out comes KBT over 1/2. That's what we know from the equipartition theorem that says that every degree of freedom of a system, is fed with KBT half of potential energy. That's the potential energy in this system. And so in the case of the Bosch sensor, if we calculate now the square root of this mean square voltage, so this is the root mean square noise voltage, is going to be root mean square of KBT over C, and what we find is 10 to the minus 4 volts. 10 to the minus 4 volts. Let's compare that with the 1.4 times 10 to the minus 3 volt in. If this is 1 volt, we get 1.4 millivolt of output signal if 1 G is acting on the sensor. And then behind that, there is this noise voltage that also is measured by the circuitry, trying to determine the C, the potential, which is 10 to the minus 4 volt. So the noise is substantial. And we cannot hope to measure micro G, microseisms with that sensor. It's going to be a bad inclination sensor if we have then a signal to noise ratio of roughly 1. And this corresponds therefore to an acceleration of 0.7 millimeter per second square at 1 input voltage. So we cannot hope to resolve more than 0.7 meter per centimeter square if the bandwidth over which the signal is evaluated is over the entire span of this RC tank. Circuit designers will put filters there that are optimized for the frequency range in which signals of importance may appear, and then they will work on designing R to make this integral, to make this, optimize this whole noise thing to values that are maybe lower, so that there may be a higher resolution. But this means that the resolution of the system at this level is only 0.7 meter per second square. And then another interesting aspect with these mechanical structures is the question about the mechanical noise. Yeah. So you have this spring, yeah, and you have this mass. Yeah. So ideally, you think that if nobody works on this mass, you know, in vacuum and nothing happens, yeah. So only vacuum, yeah, no gas hitting that mass, and then you watch this mass. And then you see it move slightly, yeah? Thermally. It moves thermally. Why does it move thermally? Because phonons, you know, cause the spring to shake. Huh? And this mass will shake because of this constant expansion and elongation and contraction of that spring. And that's a thermal phenomenon that is modeled again by an energy, a potential energy in the spring, K times delta X on average, 1/2, must be equal to the same KBT half that we have just seen before. So you can estimate the root mean square shakiness of your mass. How far does it shake back and forth? This typical delta X square can be calculated, and it is equal to KBT over 2 multiplied by 2 divided by K. So this M is wrong. Also, it needs to be a K down here. Also, you can calculate that. And what do we estimate? Delta X root mean square is 0.32 angstrom. Yeah? And that corresponds to a root mean square acceleration of 6 times 10 to the minus 3 meter per second square. That's much smaller than the 0.7 meter per second square root mean we had because of the capacitance. Yeah? So the mechanical noise is unimportant in the structure, but it will become dominant if you think of making accelerometers that are a factor of 10 smaller, that have a factor of 100, maybe smaller mass. Then it may be that or your spring constant becoming smaller also to have the same resonance frequency. So your K will become 100 smaller. And then this delta root mean square will be a factor of 10 larger. And then your A root mean square will be a factor of 10 larger too. And so nanomechanical accelerometers will suffer of mechanical noise. No doubt about that. But here it doesn't seem to be the dominant factor. And so there are some conclusions here, how to express this root mean square noise in terms of acceleration due to mechanical effects. It's given here, and here the M is correct. Now the K has been removed, and so it's a resonance frequency times square root of KBT over M. And so it says that the mass shouldn't be too small if the resonance frequency is given. If the resonance frequency is given, of course, mass and K can be changed simultaneously because omega 0 is equal to square root of K over M. And so how to increase that mass? It is by making the epi polythick. Analog devices had films of only a few micrometer thickness. They didn't have the epipoly technology. It didn't exist. And so H was only a few micrometers. So the mass were a factor of 5 smaller. And it was much harder to extract. First of all, capacitances are smaller, the noise is larger, and so on. And Bosch really hit the road with this epipoly, large, thick capacitances and masses. Well, is this example of the ADXL202, analog devices, acceleration sensor, linear, 202. Actually, it's linear, but it's for 2 dimensions. So this is used for tilt sensing for inertial navigation, where you would like to know where is what acceleration is occurring in two directions, and therefore integrating the acceleration to determine the motion, the velocity, and the position. And so it's also in computer peripherals, and the range is plus minus 2g, 1g in each direction plus some saving, some spare range. Nonlinearity 0.2% of the full scale. Noise performance 500 micro-G per square root hertz. Okay, so they say, okay, that's what we can do per square root hertz. If you need a bandwidth of such and such, then you have to think about your noise over that bandwidth. Power supply 3 to 5 volts, temperature range quite large. And then different modes of sensitivity, sensing, duty cycle sensing, or this kind of sensing where one senses the voltage of the central electrode, and that's 312 millivolts per G, and that is explained also in on the next page. Sorry, on this page here, where their philosophy is explained as found in one paper, where opposite voltages are applied on those two external electrodes in opposite directions. So it's not 0 and 1, it's -1 and +1, vice versa, switching back and forth. And if this electrode is in the center, then it will always be at 0 volt. It will be in the middle between one extreme and the other extreme, and that for all times. But if it's off center, then of course it will feel more one side than the other, and then you will have this sign, this step B function, up and down periodically, and then when this is basically flattened, rectified by taking the input from that original clock cycle, that's easy to do, then you get a constant output whose level says you exactly where the central electrode sits. If it's positive, then it's towards the up, and if it's negative, then it may be in the other direction. And so that gives you a measure of the acceleration. So this is how it is explained in this paper by Analog Devices. And Analog Devices has all kinds of sensors, numbers with number of axes, 3-dimensional, 2-dimensional, 1-dimensional acceleration, 12G down to 1.7G, sensitivities of various kinds, and so on, for a whole range of products or applications. And you can look it up on their web pages. They're of course still selling those with great success. Oops. So if we just look at this last example, that's one of the old accelerometers proposed and demonstrated by Kurt Peterson, one of the pioneers of silicon MEMS technology, then of Lucas Nova Sensor, a company that produced accelerometers. And those were built from some anodic bonded glass silicon compound with a mass that had nothing to do with these complicated etching technologies that we just talked about, these high-performance accelerometers that are now modern. But this used to be a simple seismic mass, M, with suspended by some bending beam with some bending stiffness for bending in this direction, and integrated in it were some sensing resistors. So these are piezo resistors, as we have seen in an earlier chapter 4, that are able to determine the bending. And here too we have some overrange bumper. The structure hits the ground, or it hits this upper stopper here in order to survive an excessive acceleration. So this was one of these early accelerometers, which of course looks totally different from these more modern versions of Bosch and analog devices. If we look at analog devices, it's hard to see on this picture, but there are, here is your seismic mass, M, and then here are electrodes, interdigitated electrodes that sense one motion, and interdigitated electrodes. So here of course also, and then horizontally as well. And so here it's more this kind of accelerometer that measures the capacitance by the overlap of interdigitated electrodes. Yeah, and the seismic mass is somehow suspended out here with some folded beams also that are hard to see. So this is as much as I would like to tell today. And then we have some slides on gyroscopes tomorrow. So sensors to detect what I explained at the beginning, the rotational speed of the angular rate of frames of reference. If the car starts to rotate, the electronic stability program needs to know whether the way in which it rotates corresponds to the position of the wheels with respect to the chassis of the car, or whether there might be gliding and some corrective action is needed. So this is the topic of tomorrow, and I thank you for your attention, and see you tomorrow afternoon. Bye-bye.